So solving pedigree problems is not enormously different from regular genetics problems, except because there's such a small number of offspring, there's a slightly different technique you take. But basically, you're making a genetic model and testing it. And the objective is to find the mode of inheritance of the disease. Is it autosomal recessive, R-E-C-E-S, autosomal recessive? Is it autosomal dominant? Or is it sex-linked recessive? All right. And you'll notice that we're leaving out one obvious category, sex-linked dominant. We're doing that for two reasons. One, it turns out in real life they're unbelievably rare. The second thing is it turns out to be quite difficult to tell sex-linked dominant from regular old dominant. In fact, there's a really nice problem in the problems book to get you thinking about the difference between those. If you can do that problem, you're in great shape with all this. In any case, we will not worry about sex-linked dominant in this class because it is so rare. All right? And so there's a couple of tips for solving these problems. Number one is to be careful about small numbers of offspring. That is, as a result, you can't depend on ratios like your 3-to-1 and 1-to-1 and all of that, but you rule out possibilities. That's really the best way to proceed. So again, lots of times, even in VGL, sometimes you get like close to 3-to-1 ratios because you get lots of kids. Human families, 1, 2, 3, 4, 5 kids max in these pedigrees. So you can't use ratios there. Right? This is too small a number. But you're not completely without some way to think about this. You can rule things out. I'm going to show you an example in a minute. It's like the black and white cats example that that survey problem. You can rule out certain models because you see both a black and a white kitten, even though you don't know the ratio. So there's you're using the same ideas, but in a slightly different way. Because you can't use ratios. The number of kids is too small. Number two, you assume the disease is rare. Therefore, unrelated people with the disease allele are rare. So when you're trying to work things out and you want to figure out whether something's likely or not, the assumption is these things are rare, so people carrying the disease allele are going to be infrequent. And another tip is it's oftentimes, but not always, useful to start with the people, or I should put it this way, start by out genotypes you know for sure. Well, that's a shorthand. And what I mean by that is that if you remember last time, we talked about, for example, if it's autosomal recessive and someone's affected, you know they're little d, little d. If it's autosomal recessive and you know someone's not affected, you know they're big D something. So that's a great place to start. And I'll show you an example of that in a second. So let me do an example. We're going to do this in some detail. I'm going to start with a little piece of a pedigree and then draw a bigger one. Okay. So we could, and again, when it comes to the exam, If your intuition deserts you, you can try brute force. You can see, does autosomal recessive work? Does sex-linked recessive work? Does autosomal dominant work? However, you can also use your intuition, which you get by practicing with many, many, many pedigrees, for what you can rule out. Is there something you can rule out from just right there? There is one kind of inheritance you can rule out right away. Yeah, in the back. Yeah. Mm-hmm. You can rule out autosomal dominant because why? That's right. This cannot be autosomal dominant because to be affected, he would have to have the big D disease allele, or the big M if it was Marfan syndrome. To do that, one of his parents would have had to have it, and they would have to be diseased. So that's absolutely right. You can rule out the parents are unaffected, but have affected kid, therefore not autosomal dominant. Therefore, it's some kind of recessive. Can't say for sure yet which one. So let me give you some more of the pedigree, and we'll get into some detail on this guy. You're going to want to leave us some space. Oops, that's not what I wanted to do. Sorry about that. One of these days I'll get that. I'm trying, sorry, to hit that target. There you go. All right. So leave space around this pedigree so you can mark it up, because we're going to add all sorts of notes to it. So here's the first part again. Let me get this right. 2 daughters. Daughter here. That's right. And then a pair of sons. All right. Color those. Oops, I'm sorry. He is unaffected. Sorry about that. Is that right? Yep. Okay. Let's try autosomal. Okay. So what does it mean to try autosomal recessive? And I want everybody to do this because then I'm going to, pick a name and have people report out. But I want to let you know what to do and what I'm going to ask you about. Try autosomal recessive means make me up some symbols. Big D, big A, little a. Which one's dominant? Which one's recessive? What symbols are we going to use? Make me a little allele contribution to phenotype table. Number 1. Then you take it for a test drive. Can that pedigree be explained by autosomal recessive? If you tried autosomal dominant, it wouldn't work. So I want to know, can it work? Is it possible that it's inherited in an autosomal recessive manner? That is, can you write out genotypes in a way that the parents that you've written in could have the kids that you see? That's number. So 1 is model. 2 is everybody's genotype. Can it work? And 3, we're going to work through, there's a thing called unrelated carriers, which we'll start in a very approximate way and then focus in on. I want to know how many people married into the family, how many people had to marry into the family bringing in a disease allele. So like, there might be people who in this pedigree who inherited from a disease allele from their mom. I'm interested in the people who brought the bad news into the family. All right? And so those 3 things: model, does it work, and if it works, who had to bring in a little d, which I kind of gave away the first part. But anyway, all right. So think about it, talk to your neighbor, and then we'll work this